Howdy, howdy, howdy. So in this video, I'd like to talk a little bit about the order of operations when you're dealing with algebra. So let's talk about what I mean by the order of operations first. So there's the order of operations for arithmetic. And so in our case, we'll be looking at real numbers, arithmetic on the real numbers. So let's take a look at this. So a lot of textbooks and a lot of people use a particular mnemonic for the order of operations. I'm not a fan of that one, so I use a different mnemonic with a different acronym. Okay. So the acronym I like is either GEMA or GEMA or GEMA or Great Elephants Multiply Accurately. Sure, that works. So here's what they stand for. G stands for grouping symbols. E stands for exponents. Okay, M stands for multiplication. And then I'm just going to put in parentheses here, and division. And I'll explain that in a moment. And A stands for addition. And again, in parentheses, I'll have and subtraction. Now, the order of operations it's just something we agree on as a society of mathematicians, that this is going to be how we interpret certain numerical expressions. So, for example, if I say, hey, let's evaluate 2 times 3 minus 5 to the third power, well, the order of operations says first I do what's inside the parentheses, which is 3 minus 5. Then I deal with the exponent, which is cubing the negative 2. So I'm just going to write it out 3 times to emphasize what's going on here. So negative 2 times negative 2 times negative 2 is negative 8. And then finally I do the multiplication. 2 times negative 8 equals negative 16, and there is no addition or subtraction to do at this point. This is just something where we've agreed that that's how you interpret this expression. 2 parenthesis, left parenthesis I should say, 3 minus 5, right parenthesis, to the third power is interpreted this way. If you were to go to a different group of mathematicians from a different planet, let's say, and let's say they for some reason use the exact same symbols we used, but a different order of operations, that would be valid. This is just, it's more like a grammar than a mathematical property or something like that. And this is a little weird because we're not used to that too much in math. A lot of times in math, things are purely the result of properties, what happens to be true about what we're dealing with. Okay, so let's talk a little bit about the multiplication and addition parts here. So first of all, we have to consider the fact that division is just a special kind of multiplication, essentially. So if I say 5 divided by 2, that's the same thing as 5 times 1/2. And so it is reasonable to think of division as multiplication by a reciprocal. In this case, you would get 5 halves, or 2.5, or whatever. Similarly, subtraction can be thought of as addition. So if I said, how about 7 minus 3, that's the same thing as 7 plus negative 3, and we get 4. So since subtraction is equivalent to a form of addition, we can treat it as the same as addition when it comes to this hierarchy. Finally, one note, and that's each of these has an order within it. So grouping symbols, we work inside out. Let's look at an example of that. So let's say I was to evaluate, or I were to evaluate, I should say, 2 minus 5 plus 3 times 4, and then multiply that by 3 minus 5. Okay. So then what we would do is we'd look at grouping symbols and go toward the insidemost part. So that would be this 5 plus 3. So 5 plus 3 is 8. Okay. So now within these parentheses we have two sets, and now the order doesn't actually matter. We can work on this left one first or this right one, it doesn't matter, and that's a result of commutativity of multiplication. So let's deal with working through this group here. So we have 2 minus 8 times 4, so the order of operations says the 8 times 4 comes first. So we have 2 minus 8 times 4 is 32. Okay. And now we would have 2 minus 32 is negative 30, and 3 minus 5 is negative 2. So now I'm done with all the grouping symbols, and now I can go ahead and do this multiplication, and I get positive 60. Okay, hopefully I haven't made a mistake here. If I did, I'll make a note of it later when I add captions. Okay. So with grouping symbols, we work inside toward the outside, or inside to outward. This is looking really kind of ugly here. Let's clean this up. And then just a comment about the fact that, I said the order didn't matter at one point. There are a lot of times where orders actually don't matter. Here, when I had grouping symbols and we didn't have one inside of the other, so here and here, two different sets of grouping symbols, but neither was inside the other, the order didn't matter. Before I talk more about ordering of things, I want to make a note about this set of parentheses here. This is one of the reasons I don't like the more common mnemonics for the order of operations. Those involve using P for parentheses often, and here we have a set of parentheses that does not mean you do it first. These parentheses are they're not serving as grouping symbols at this point. They're just forming as a multiplication symbol. So when we talk about grouping symbols, it's not just the symbols themselves, but it's if the symbols are being used for the purpose of grouping. So we've already seen parentheses. Other examples involve brackets and braces. Those pretty much function the same way as parentheses do when used as grouping symbols. But some others are absolute value bars, but also things like the radical symbol, okay, and even a division bar, right? If I have a division bar and I have things written on top and the bottom, what this has done is this has formed two groups. We have the top and the bottom. And so if there's any operations going on inside the numerator or inside the denominator, those need to be performed before we actually do the division. In terms of exponents, you really just use any grouping symbols to determine this. So let's look at another example. So let's say I were asked to evaluate 2 minus 3 to the third power, and then that is all raised to another power. Now, at this point, we have to rely on grouping symbols, because if I put parentheses, let's say, around this, and then make that squared, then what that means is I have 2 minus 3, which is negative 1. And then I raise that to the third power and then square that. So then I would have negative 1 times negative 1 times negative 1 is negative 1. And next I square that, and I get negative 1 times negative 1 is 1. Okay, but if instead I had written 2 minus 3 cubed, and then the 3 is squared, well, what that means is I evaluate the 2 minus 3 and get negative 1, but the negative 1 is raised to the 3 squared power, and so at this point, the position of a superscript is a grouping symbol on its own. There's actually a little pair of parentheses in here that we don't actually write out usually, but are implied by the fact that 3 squared is all in that superscript position. So then we would have negative 1 to the 9th power. Okay, and so negative 1 times 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 negative 1, I think I got that right, is negative 1. Okay, so in this case, we have to rely on the operations being either explicitly grouped, like up here, or the position being clear. If one of those two things isn't the case, you don't have some parentheses telling you what's going on, or you can't clearly see what's in the exponent position, the superscript position, then it would be ambiguous, and we don't like ambiguity. Okay, next up, multiplication and addition both have the same rule. For the most part, people treat it as you go left to right. However, multiplication and addition are both commutative. So you actually have an option there in terms of the order. Now, it does have to be converted to addition or multiplication before you can start changing the order of things. Right? 5 divided by 2 is not the same as 2 divided by 5. However, 5 times 1/2 is the same as 1/2 times 5. So we get commutativity after we've converted them to either multiplication or addition. So in the usual mnemonics that separate multiplication and division and separate addition and subtraction, they have to say left to right, because when it's written as division or subtraction, you do have to follow the order. But once it's written in terms of multiplication or addition, you can move in any direction you want. One last comment about why I don't like the other mnemonics you see out there is precisely because of the separation of multiplication and division and the separation of addition and subtraction. That gives the impression that there's a hierarchy between them. Every few months or so, I see on social media a problem that involves the fact that people make this mistake. So there'll be a lot of arguments about things like this. So 12, let's say, times 6 divided by 2. If we are to follow the order of operations, oops, I don't want it to do that. We'll write it like this. There we go. If we were to follow the order of operations using either the fact that we can rewrite this as 12 times 6 times 1/2, or I'll show another way in a moment, then it becomes clear what this is. Okay, well, I'm just going to have 12 times 6 times 1/2, and I can do these in any order I want. So I'm just going to go ahead and do 12 times 1/2, and that gives me 6. And so my answer is 36. Okay, now using the other typical mnemonics, where they would leave it as division, they would say move left to right. So 12 times 6, 12 times 6 is 72. And then you have to divide by 2, and 72 divided by 2 is 36. Okay. There will be people, however, that think that multiplication has to come before division, and so to confuse someone, all you would have to do is change this order slightly. Okay, so let's say over here, we'll redo this, and instead of saying 12 times 6 divided by 2, what if I do 6 divided by 2 times 12? Okay, this is the one that throws people off, because if I move left to right, it's no big deal. 3 times 12 gives me 36. Or, again, if I instead convert it to multiplication, so I'd have 6 times 2 times 1/2, sorry, times 12. I have 6 times 1/2 is 3, and 3 times 12 is 36. Or I can do what I did before and group the 1/2 and the 12 together and get 6 times 6 to get 36. It doesn't matter. What the problem is there's a lot of people that they think multiplication has to come first, so instead they treat it as if it was this. Sorry about that. Okay. So they treat it as if the 2 times 12 part were in parentheses. And so they end up with, 6 divided by 24, which becomes 1/4. Okay, so if it were written with parentheses, then yes, this would be correct. But without the parentheses, it's evaluated the way we see in this first line here. This is also why the division bar is fairly useful. Okay, if you wanted to mean this second one here, but didn't like writing it with parentheses, well then what you can do is you can use the division bar, because the division bar is itself a grouping symbol. And so then you would have 6 divided by 24 again, and you would get 1/4. If we stick with this as our order of operations and use this mnemonic, in my opinion, you're less likely to run into problems like what people tend to have occur when they deal with situations like this one below. So this is the order of operations for arithmetic. It works the same way for algebra. Okay, remember that when you have a variable, let's say, in algebra, so let's say you have 7x squared, and you're supposed to evaluate this for x equals -9, let's say. What that's saying is you simply replace x with -9. Now, x is supposed to be squared. All of x is supposed to be squared, so that means I have to put it in parentheses as a grouping symbol. I'm grouping the negative with the 9, so that I don't want it to say like 7 minus 9 or something, right? So I have 7 times -9 squared, so that's 7 times -9 times -9, so that's 7 times 81. And then let's see, so 7 times 81, and that is going to be 567, I believe. So in this case, we were given a value for x, and so it makes sense to say that you know, the arithmetic and the order of operations works the same with algebra as it does with real numbers. But even if I hadn't told you what x is, remember, x stands for one of possibly many different values, but all those values are still numbers. And in this case, real numbers. But if we were in a different course, maybe a more advanced course or something, you might have x might be a complex number, and so therefore might be imaginary. You can deal with things like quaternions even, but the point is that they still represent numbers. Now, when you go beyond algebra, for example, let's say linear algebra or group theory or other types of things, well, then they might not be numbers, and now the things like order of operations, the properties of operations, the actual operations themselves, those are going to change. And so when you switch from x standing for numbers to x standing for other things, then you're going to maybe have different things going on. But for now, variables are simply representing numbers, and therefore things work just the way we want them to. I hope you found this helpful, and have a lovely day.